This is a tutorial based on AQA Science Core sections 2 and 3 about using energy and electrical energy, paying for electricity bills, Sankey diagrams and energy flow diagrams. It's got quite a lot of information in it, but a lot of it is relatively straightforward. Conservation of energy is an important principle in physics. Basically it states that no energy is ever lost, it is only ever changed from one form into another. Okay. That's it. So whenever we're looking at energy flow situations, if we're not having 100% energy transfer, then we've got something wrong. Okay, and usually we may well have missed out. For instance, heat transfer. Energy is often lost as heat. That's quite often one of the main forms of energy wasted. Right, so we've got a list of the main types of energy. Most of it is fairly straightforward. What I'd like to comment on is gravitational potential energy. Make sure you at least write full wording out once in a particular question, so gravitational potential energy, not just potential energy, as there are many forms. So gravitational potential energy, and then once you've written it in full once, you can then use the abbreviation GPE, and that's energy due to height of something above a surface. Strain energy is a useful one, and that's stored in a rubber band or a catapult or something like that. And chemical energy is energy stored in food or fuel, or indeed, for instance, a battery as well. That's chemical energy. So just watch out for these ones. They're quite useful. Batteries don't store electrical energy; they store chemical energy, which is then transferred into electrical energy. So make sure you're happy with the different energy types and principle of the conservation of energy. Right, energy flow diagrams. These are fairly simple. Generally speaking, sort of year 8 work, so this is sort of grade D material really. Everyone should be able to do this. They'll be on the core paper and may well be on the higher one as well as a sort of introductory question. So if we look at an energy flow diagram for a light bulb, a TV and a swing in the park, I'll give you a few minutes to think about this, so press pause and then move on to the video when you think you have the solutions. So pause now. Okay, solutions. The light bulb. Electrical energy goes to light plus heat. Fairly straightforward. The television. Electrical energy goes to light plus sound plus heat. The swing in the park. Gravitational potential energy goes to kinetic energy. And that again goes to gravitational potential energy because the swing keeps going backwards and forwards. Just read the question, see how many energy changes there are, but generally GPE goes to K in the swing. There are many other examples to use, but the idea is that we use an arrow. We can't tell which energy is bigger. We don't know whether the light or the heat energy is larger in this particular diagram. As a rule, we put useful energy first and then wasted energy second, and it's not an equal sign but an arrow because it's an energy flow. Electrical energy is changing to like this. Moving on. Sankey diagrams. These are much better. They show the not just which is wasted and which is not wasted, which is useful, but they also show the sort of sizes of the energy. There are two types of Sankey diagrams you would have to do. One is an accurate one like this, and one is a sketch. So I'm just going to run with this one. Even if you do a sketch diagram, you should try to make the arrows roughly representative of the size of the energy. With a scale diagram such as this one, then we're looking here at one square on the diagram equaling, in this case, 1 joule. There's no reason why it should be 1 joule. It could be 1 square is 10 joules, 1 square is 1,000 joules. Look at the question and see what's going on. I've used straight lines to represent the diagram as it's slightly easier to draw this, and useful energy goes on the top, going out to the right, and wasted energy goes out at the bottom, and everything is to scale. So you have to make sure you've given yourself enough space to draw all the arrows in the correct places. Using this one, because it's already drawn for us, which will be a sort of grade C type thing, we'll be using this diagram to work out values and ultimately something called the efficiency of the device. Okay, we can use Sankey diagrams to record and measure the electrical energy, in this case electrical energy in, the useful energy out, and the wasted heat out. This particular diagram has a scale of 1 joule equals 1 square. That isn't necessarily true in all diagrams. Make sure you read the information. It could be 1 square equals 10 joules, 1 square equals a kilojoule. Just make sure you read the information and therefore count the squares correctly. So pause the video and work out A, B and C. So pause now. Right, we've now got the answers, so we'll just go through the answers quite quickly. It's a relatively straightforward Sankey diagram, this one. So A, electrical energy in. If we count the number of squares, we see that we've got 13. As 1 square equals 1 joule, that gives us 13 joules. The useful energy out is composed of 2 forms of energy, light and sound. Sound energy is 3 squares, which is 3 joules, and light energy is 1 square, which is 1 joule, giving a total of 4 joules. And the wasted thermal energy or heat energy out is 9 squares wide, which is obviously 9 joules. A useful check is that 4 plus 9 equals 13, so therefore 13 joules of electrical energy in equals 13 joules of energy out. As we said before, there's the principle of conservation of energy, so the total energy should be the same for both in and outputs, and so therefore there should never be any difference between the two. So 13 joules in, 13 joules out, a useful check to make sure you've done everything correctly. If we now move on, we can have a look at other uses for Sankey diagrams. We can use the diagram to help us calculate efficiency, or we could just have efficiency equations on their own. Efficiency is how good an appliance is at transferring energy in a useful way. So therefore we're only actually interested in the 4 joules of useful output energy compared to the input energy. There's the equation which is given to you in the book, or the formula sheet, useful energy out over total energy in. We multiply it by 100, gives us percentages. It doesn't have to be a percentage, but it's much easier for us to understand percentages. The formula is given to you, so you don't have to learn it, you just have to use it. It's 4 over 13, which equals times 100, which is 31%. If you get a number bigger than 100%, you've gone wrong. So that's a useful check again. Right, moving on to the formula triangle. We've seen these before in other tutorials, and depending on what you want to find out and what information you've given, you can use this triangle to rearrange things. So if we want to get useful energy out, we come up with the useful energy out and we give it its efficiency times total energy in. Now in this case it has to be a fraction. We'll come to that later. So if we have a percentage, we have to divide it by 100. If we want to know the efficiency, this is the one that we've normally come across. Efficiency is useful energy out over total energy in. And similarly, if we want total energy in, it's useful energy out over efficiency. Again, it's a fraction. Right, we'll do some examples of that, and we'll see what happens. So the first thing is that where does all the wasted energy go? Typical end of question, really. Usually sort of a part B or D or something like that, and it all eventually is dissipated into the surroundings as heat and warms up the surroundings, or is lost into the surroundings as heat. So it's a useful 1 marker. Right, efficiency, another example, slightly harder. We've got an electric motor is 25% efficient. The total energy is 3,200 joules. What's the useful energy out? So we have to rearrange the efficiency equation and change the 25% to a fraction for this to work. Otherwise we'll be multiplying by 25, which would be giving us a huge number rather than a smaller number. So useful energy out, it's a quarter of 3,200, hence 0.25 times 3,200 equals 800 joules. If you times it by 25, you'd have a massive number, you'd have more energy out than you had in, which can't happen. So remember to change percentages into fractions. So 0.25 times 3,200 is 800 joules. Intuitively it kind of works really if you think about it. Something's 25% efficient. It's only giving you a quarter of what had in. Right, moving on, you have a go. Okay, so we've got 2 questions. Pause the video, or give yourself a few minutes, have a go at working them out. Use the formula triangles as necessary. These are around sort of CB, A question. Question 1 is a sort of grade C question, and 2 is a sort of B/A question. Okay, so pause now. Right, answers. Question 1 is straightforward. Efficiency, we're doing it as a percentage. So useful out, 20 divided by 80 in times 100, 25%. Fairly straightforward. Probably just 1 mark. A machine is 40% efficient and the useful power out is 1000 watts. What's the total input power? Now the equation is just the same for power and energy. It's the same pattern. All we've done is just swap power in for energy. There are 2 equations on the formula sheet. One for energy and one for power, but they're used in exactly the same way, so I'm not going to go through formula triangles for this one. Using the formula triangle, we find that we get input power equals useful power out over efficiency as a fraction. So 1000 over 0.40 gives us an input power of 2500 watts. Obviously the input power has to be more than the output, the useful output power, because we also have wasted. So you can think carefully about the numbers. That's a grade sort of B/A question, and again using power instead of energy, but the same sort of ideas. Energy and power, there's a special equation that links them, and we have power equals energy divided by time, or P equals E over T. We've been using these units for quite a while now, so power P is units watts, energy transferred, or E, is unit joules, and time standard unit is seconds. These are all standard units, hence we change kilojoules to joules, we change minutes to seconds, and so on. Right, we have another formula triangle, so if you want to know E, cover the E up and we have P times T. If you want to know P, we have P E over T, and if you want to find T, we have E over P. We've been using such triangles before, and you should now be becoming relatively familiar with them and fairly confident, I hope. And you should be able to turn any equation on the formula sheet into such a triangle. Right, we can use that for power questions. So again, pause the video, give yourself a few minutes, have a go at the questions using the formula triangle, and just see how it goes. Okay, so pause now. Answers. Okay, so how much energy does it transfer in 30 seconds? Well, energy is power times time, 5000 times 30, 150,000 joules, or 150 kilojoules. Relatively straightforward. There's no real rearranging. That's the equation given to you in the formula sheet, so 1 mark. Okay, a low power light bulb, 20 minutes, transfers 18 kilojoules of energy. What's its power? Right, a little bit of work to do here. First of all, we have to change minutes to seconds and kilojoules to joules. So 20 minutes is 1,200 seconds, and 18 kilojoules is 18,000 joules. Nothing too difficult, but you just got to remember to do it. Rearranging the equation, we get power equals energy over time. 18,000 over 1,215 watts. 2 marks, one for the conversions, one for the correct answer. Right, paying for electricity. The electricity companies don't use joules for energy, or watts for power, or seconds for time. They use kilowatt hours for energy, kilowatts for power, and hours for time. The reason being that we use that much energy that they need a unit which is manageable. There just would be billions of joules, those are just huge. So to make it a manageable unit, they use the kilowatt hour. So we have to now convert all powers into kilowatts and all times into hours. How do you know when to do that? Well, you just look at the question, and if it talks about paying for electricity, then this is the units to use. And we get the main unit called the kilowatt hour. As an example, 1 kilowatt hour is the energy transferred by a 1 kilowatt device for 1 hour, 1 times 1. You could have a 0.5 kilowatt device on for 2 hours, and that would give you the same amount of energy overall, 0.5 times 2. So there's all sorts of combinations. Cost of electricity. Okay, so we'll just run through this. We've done work like this in the lesson, so this is just a sort of review. 1 kilowatt hour costs 15 pence. Work out how much the following cost. So 2 kilowatt heater on for 3 hours. I'll go through this one with you and then we'll pause it later. So what we do first of all, we do energy equals power times time, and we work out the energy in kilowatts, so hours. So 2 times 3 equals 6 kilowatt hours. We know 1 kilowatt hour is 15p, so the cost is 6 kilowatt hours times 15p, which is 90 pence. Okay, have a go at B and C. Okay, so pause the video now. Right, here are the solutions. What we've got to do is change 500 watts into 0.5 kilowatts, and 5 hours 30 minutes into 5.5 hours. Once we're in the correct unit, we multiply the numbers together to get our 2.75 kilowatt hours. And then we multiply that by 15 pence to get 41.25 pence. You should really set it out with both separate lines, okay, rather than just put times 15 on the top line. It's better to have two separate calculations so that we all see what's going on. Right, question C. We've got 4 lights of 100 watts, so we change it into kilowatts and multiply by 4. So 100 watts is 0.1 of a kilowatt, so it's 0.4 kilowatts. The microwave, well, we're going to stick with the lights at the moment. So the total energy used is energy is power times time. They're on for 5 hours, so 0.4 times 5 is 2 kilowatt hours. 15 pence a kilowatt hour, so that's 30 pence. We can then jump onto the microwave, or move on to the microwave calculation, and again 1200 watts will change into kilowatts, 1.2 kilowatts. 30 minutes will change into hours, 0.5 an hour, so that gives us 0.6 kilowatt hours in the microwave oven at a cost of 0.6 times 15p, which is 9 pence. So the total cost of the light bulb and the microwave oven are 39p. You could change the order of doing these calculations. I find it easier to work out each component separately and then add up the total cost at the end. But read the question, see what information they want and how they've set it out. All those questions are sort of C/B standard questions. Okay, this is a little bit more challenging. It's sort of you've given a certain amount of money to spend and you have to work out how long it will last. So first of all, have a little think about this. Pause the video for a few minutes and see if you can actually get the solution. So pause now. Okay, the solution. The first thing you've got to do is calculate how many kilowatt hours you can actually afford for £5. What you have to do is change £5 into pence. It's much easier to work in pence, kilowatt hours in pence. And we get 500 pence divided by 20 is 25 kilowatt hours. So you can have 25 kilowatt hours at 20 pence per kilowatt hour. So I don't think that's particularly too difficult. Right, now once you've got that, you can then work out how long it will last. So time equals energy over power, that's from the formula triangle. So for the heater, it's 25 kilowatt hours over 3 kilowatts, which is 8.33 hours, or 8 hours 20 minutes. So with £5 you can only run a heater for 8 hours 20 minutes, which in winter isn't a great deal of time. Right, B, or alternatively you can put up with the cold and put a jumper on and run your television at 25 divided by 0.5 kilowatts for 50 hours. So you can watch plenty of television, but you'll be a little bit chilly. So you may well have to make decisions like that at some point in your life. So let's hope not, but there we are, people do. Right, if we move on from this, we can see that we've got the final one about, again, cost of electricity. Most people have electric meters and pay for the bill at the end of the month. So the meter will click away quite happily as you use your electricity. So if we have a look at this one, we can see 2 readings, one at the beginning of the week and one at the end, and we can work out how much this person spent. We subtract the largest number from the smallest number, and we see they've used 88 units or kilowatt hours of energy, 16 pence each, so it's £14, 8 pence. Fairly cheap actually, not too bad. During the week you've got a 2,600 watt kettle, it's on for 3 hours. How much energy did it use? We've done this, it's fairly simple, fairly straightforward answer. Energy is power times time. Change 2,600 to kilowatts, 2.6 times 3 hours, 7.8 kilowatt hours. You could then work out how much that costs by multiplying that answer by 60. So these questions can sort of build quite quickly from relatively short questions to sort of fairly longish questions, but each stage isn't particularly difficult, and that is the key to all of these sort of questions. Go through each stage at a time, making sure you set it all out neatly and you've got your units correct. Right, well that's the end of this tutorial. I hope it's been useful to you, and there'll be further tutorials